Good morning, everyone. I'm Shriram Pandian, and I co-authored this paper with my professor Naresh Shetri, both from the Cybersecurity Department at Rochester Institute of Technology. Today, we are presenting our work on dataRLsec, which stands for Data Reinforcement Learning Security. This research tackles one of the biggest threats in AI today. What happens when attackers poison your training data? So let's jump right in. So, what we are trying to solve here, data poisoning attacks are becoming massive problem as AI systems get deployed everywhere. Hackers inject malicious content into the training datasets, and this causes models to make wrong decisions that are really hard to detect. Our main contribution is an algorithm we call DWBC, density ratio weighted behavioral cloning, combined with hash verification for security. The key innovation is pretty simple conceptually but powerful. Instead of treating all your training data equally like traditional behavioral cloning algorithms do, we weight each sample based on how similar it looks to small set of clean data we trust. And this whole framework is designed for offline reinforcement learning, which means learning from pre-collected data sets rather than interacting with the environment. The application here is protecting any AI system that learns from potentially compromised data. Think autonomous vehicles or medical diagnostics or financial systems, you name it. Let me point a picture of why this problem is so urgent. Data poisoning works by injecting carefully crafted malicious samples into your training set. What makes this scary is that the results look normal, but the model seems fine. But as you can see, it can make wrong decisions with a lot of confidence. This is a classic garbage in and garbage out problem that we look into the computer science era. The impacts are real and they are happening now. Why I say that? In cybersecurity, we are seeing IP theft and autonomous system hacking through these attacks. Techniques include label flipping, where attackers just change the labels on legitimate data, and backdoor injection, where they plant triggers that activate malicious behavior only under specific conditions. In healthcare, imagine a diagnostic AI that's been fed falsified medical knowledge. Patients get wrong diagnosis. In finance, poisoned prediction models could trigger massive losses or enable fraud at scale. These aren't hypothetical scenarios, I'm saying, but the researchers have recently shown that it is possible, and a lot of medical large language models are highly vulnerable to these exact attacks. Before presenting our solution, let me quickly contextualize where we fit in the research landscape. We surveyed recent work on found several interesting approaches, but they all have gaps. Deep reinforcement learning systems and crowd sensing have been shown to be vulnerable. Frameworks like Truth Finder can help, but they only limit the damage. They don't prevent it. There is a work on adversarial RL like DPAD music, but that's designed for semantic communication networks, not the traditional architecture where most real systems operate. And what about federated learning? It is interesting because it enables privacy preserving training, but it creates a new attack surfaces. Malicious clients can still inject poison gradients, and the research constrained devices struggle with the computation cost of those detections. So peer-to-peer federated learning using Markov decision process for client selection but lacks centralized oversight. The fundamental gap we identified is that there is no comprehensive practical defense mechanism specifically for offline reinforcement learning with contaminated datasets. That's exactly what dataRLsec try to address. For our experiments, we needed a rigorous testbed, so we chose JOCO, which stands for Multi-Joint Dynamics with Contact. It's basically the gold standard for robotics and reinforcement learning research. Our setup uses the half-cheetah agent, not only that Hopper, Walker 2D, and AND models. This is simulated with a lot of physical movements, and we are using gym libraries developed by Google. But to early access and to make it easily available on your devices to replicate these experiments, I try to say that use Minari, which is very good environment and bounded library. So why Mujoko specifically? There are three reasons for it. It's free and open source, and it has optimized physics simulation with realistic contact dynamics. And the good thing is it provides 3D visualization, which makes it easy to see what's really happening under the poison data. To design effective defenses, we need to understand the full threat landscape. Let me break down into three categories. First is attack types. We have stealth attacks that operate below detection thresholds, model inversion that extracts sensitive training data, direct training data poisoning, which is our focus here. And the backdoor poisoning, where triggers get embedded for later activation, is also a concerning problem. Second, the consequences. Degraded model accuracy means more mistakes over time. Amplified vulnerabilities create new attack surfaces. Wrong classification can be catastrophic in safety critical systems. And ultimately, you risk complete system compromise. The third is this is where the defense gets really hard. The detection challenges. Poison samples often have sample specific triggers that only activate under certain conditions. They are invisible to human experts, and even clean label attacks are particularly nasty because the label looks so correct, but the features are manipulated. So, this taxonomy directly shaped how we design our four-stage architecture. So before showing the architecture, I really wanted to show this slide. So you can see in the top, the two models are performing very well, Half Cheetah and Walker 2D. And below, as you can see, under poisoning, they are basically fall down and nothing. They're unable to do anything basically. So as you can see, there is nothing wrong with the code or there is no syntax error, but the degradation is massive. The movement becomes completely erratic. The agent can barely maintain stability, accuracy drops through the floor. So we want to address this issue, and how we can going to do that using the four-step architecture that we developed with the cryptographic hashing. So we'll look in the next slide. So now here the heart of our contribution. I know this flowchart looks complex, so let me walk through it stage by stage. Stage 0 is our security foundation. We do cryptographic hash verification of our reference dataset before anything else happens. If that hash doesn't match what we store, we abort training immediately, no exceptions. This prevents attackers from compromising our ground truth, but the stage one trains the discriminator network here. Think of this as a data quality inspector. We train it to distinguish the trajectories from trusted clean reference set versus trajectories from the potentially contaminated data set. It's a binary classifier basically, so that learns to output the probability that any given trajectory came from the clean distribution. Stage 2 computes weights using those probabilities. For each trajectory in our contaminated dataset, we calculate the density ratio. This transforms those probabilities into importance weights. If the discriminator says something looks 90% like clean data, we take it as high weight. If it says 10%, we take it as low weight. We also want to clip it so that we can handle the extreme values. And the stage 3 is training the actual policy itself, which is very important. So that's where we call it as weighted behavioral cloning. We use these frozen weights to weight the loss function, so clean looking trajectories contribute more to training and suspicious one contribute less. The output is a robust policy that's resistant to data poisoning. The beauty here is it's fully automated and no manual inspection needed. Let me explain the core math that makes this work. Traditional approaches treat all training samples equally. Think of a traditional behavioral cloning algorithm. Every trajectory gets the equal weight in the loss function, but when you have data poisoning, you got a mixture of clean and adversarial data. Our key insight comes from important sampling theory in statistics. We train the discriminator function d of tau that outputs a probability of trajectory tau came from our clean reference distribution. Then we compute the density ratio using the formula R equals d of tau divided by 1 minus d of tau. So how this works is basic mathematics that we are using. This comes from the Bayes theorem. If d of tau is close to 1, meaning it looks very clean, but the ratio becomes very large. If it's close to 0, meaning it looks suspicious and the ratio becomes very small. Then we apply clipping w equals max of epsilon comma min of R comma C. So where C prevents any single trajectory from dominator training and epsilon ensures we never completely zero out any samples, which maintains the robustness to false positives and makes the model stable. The density ratio weighting is grounded in decades of statistical research, but applying it to offline RL for cybersecurity is what I consider the best thing. Let me be completely transparent about our limitations. First, we require access to small verified clean reference set. There is no compromise there, and it depends entirely on that small data set. And if that reference set is compromised or doesn't fully cover the state space or discriminator learns a wrong notion of clean, second, we assume that static contamination or discriminator is trained once on fixed data set. If an attacker continuously adapts their poisoning strategy, we might not generalize it. So what's the third thing is there is a computational overhead. We are training two networks instead of one, which increasing the training time by roughly 50 to 100%. Fourth is while we handle common poisoning strategies well, high list of sophisticated attacks specifically designed to full density ratio estimation might still be succeed. So the main limitation is around the static nature of this whole process. So we need to uh, fix that in the future work, obviously. So looking forward, we have several directions to extend this work. On the enhanced side, we want to incorporate oral modules that leverage environmental dynamics. Right now, a discriminator only looks at the state action trajectories, but we could also be used to reward signals and transition dynamics to catch more subtle poisoning. We want to adapt this to online domains where contamination continuously shifts, making the discriminator adaptive rather than static. We're also working on improving this density ratio estimation itself to reduce the computational overhead. For validation, we plan to evaluate on safety critical domains like autonomous vehicles in car law simulation and healthcare treatment recommendation systems. And we want to combine the DWBC with the complementary defenses like adversarial training to create defense in depth. The broader vision is making robust RL a foundational component of trustworthy AI systems. Let me crystallize our three main contribution. First, this is a novel algorithm. This is what the first integration of density ratio weighting with the hash verification for making sure the small reference data set is clean and it's not manipulated by the attackers. And previous work looked at this concept separately, but combining them in the first stage architecture is new. And second, the Mojoko benchmark we showed, I ran more than 500 experiments for more than 1,000 hours. So it gave us a very good insight about how these will react to various poisoning methods. So our results show that performance within 10 to 15% of clean baseline when 30% of training data is poisoned. So standard behavior cloning degrades by over 60% under the same condition. So it means that our model is performing very well and able to distinguish between the poison data and the clean data, which is a good success for the static algorithm architecture. So the third thing is we have open sourced the code and provided the detailed implementation guidelines and documented everything in the GitHub. I'm happy to share it at the end of this slide. To wrap up, we propose dataRLsec, a comprehensive, robust offline reinforcement learning framework designed specifically for safety, security, and reliability against data poisoning attacks. Our DWBC algorithm with hash verification enables secure policy training even when you can't trust your training data. The four-stage architecture provides both theoretical soundness grounded in statistical theory and practical implementability. We demonstrated effectiveness in Bujoko with half-cheetah benchmarks showing we can maintain near optimal performance even with significant data contamination. Future work focus on dynamic environments, defense synergy, and validation in real-world safety critical systems. As AI get deployed in critical infrastructure, this kind of security at training phase becomes essential, not just useful. Thank you all for your attention. I'm happy to take any questions about our methodology, the mathematical foundation, experiment results, limitation, or future reduction. If you like to follow up after this session, please take note of my email and ask me any question if you have any. And I'm happy to share the GitHub link for the actual experiment. I would believe that it will be also established in the main website. Please let me know what questions you have. I'm happy to looking to answer all your questions. Thank you so much. Have a great day and take care.